the previous module we have talked about amplitude modulation, which is basically a linear modulation. Amplitude modulation had a lot of different variations. We talked about the one in which we suppress the carrier and transmit it, used for ad hoc communications, and then we have AM broadcast, in which we send the carrier, that is AM with the large carrier, so we send the carrier with it, and then TV video signals, that is in terms of vestigial sideband modulation. So that is something that we have covered so far. Assuming this is our message signal and this is the carrier, both are single tone. Carrier is definitely at higher frequency as compared to the message signal. So in amplitude modulation, based on the amplitude of the message signal, an envelope is established which is transmitted. Presently, we are going to talk about some non-linear modulation scheme, angle or exponential modulation. Angle modulation has basically two different variations. The first one is frequency modulation, and the second one is phase modulation. Now, FM also has a number of applications, including the one that you have with you in your vehicles or handheld radio devices. That is the FM broadcast, operating at around 88 megahertz to 108 megahertz. And also in TV signals, specifically audio signals of TV, they use FM modulators. And also it's used in cordless telephone. Phase modulation, it is primarily used in digital communication, including digital video broadcasting terrestrial. So when we're talking about phase modulation or frequency modulation, both of them are dependent on the message signal. If the message signal has a high amplitude, the modulated signal at that instant would have a high frequency. And when the magnitude of the message signal is low, then the frequency would be low. So the maximum and the minimum frequency is basically governed by the positive peak and the negative peak of the message signal in frequency modulation. In fact, frequency modulation and phase modulation are basically linked together by means of calculus. So often it is, for a very generic or complicated signal, usually it's quite difficult to, just if you see AM signal or FM signal, you would not be able to distinguish which one is which until and unless you know the scheme behind which it was transmitted. So we will elaborate on both of these schemes in today's lecture. So when we're talking about modulation, we have amplitude modulation and angle or exponential modulation. So in amplitude modulation, if we send a signal S of t, the amplitude is varied with respect to the message signal. This is varied with respect to the message signal. So in angle modulation, this amplitude is kept constant, while this angle is varied with respect to the message signal. That is the major difference. So what are the benefits of moving from AM to FM, and what are the drawbacks? There is a common fallacy which says that the bandwidth of the angle modulation might be less than the AM, but this is not the case. At best, it is equivalent to AM, and usually it is greater than the AM. Now, if we are going to lose, we are spending more on the bandwidth. So, what is the benefit? So, one may ask. So, the answer to that is robustness, or what you call the resilience of this modulation schemes in terms of noise. So, if we are sending something over the air and then we are receiving modulated, the amplitude would be affected by the ambient noise on the transmitter and receivers. So once the amplitude is attenuated or degraded, so we will lose the information. But in angle modulation, the amplitude is not conveying any information. In fact, it's the phase which is conveying information. So that's why it is more resilient in terms of noise parameters. So we lose on the bandwidth, but we gain higher quality or higher capacity of a reliable data communication. So why do we call it angle modulation or exponential modulation? Usually, as I mentioned, that the message is basically conveyed inside that angle, right? But this can also be written in terms of a real part of exponential j theta of t. So if you open this, it will become cos theta plus j sine theta, but the real part of it would be simply this one. So that's why it's also called exponential modulation. One of the most significant aspects of angle modulation is to understand the concept of instantaneous frequency. The message signal is basically embedded inside that general angle. So if we plot the angle with respect to time, so it would show some kind of a non-linear behavior. So this is theta of t with respect to t. Assuming we pick this point and a small interval after it. So extend a line crossing through it like that. This line will be intercepting the y-axis at theta naught. We may call this as omega ct plus theta naught. So this is something which is showing a linear behavior, and since it's showing a linear behavior, we have observed this over here in am omega ct plus theta naught. So if we take the derivative of this one, so with respect to time, so d by dt of this one, so we would simply have a constant which is omega c. But over here, the angle is the generic angle is constantly changing. So if we start at this point and we take another increment after delta t, so we say that we are trying to find the rate of change of this angle with respect to, so let's say delta t and delta t plus delta t, right, with respect to delta t, right. So this is something which we call as rate of change. Since it is in f, we can just multiply 2 pi in the denominator. If we let delta of t approaching 0, so that would mean that if we limit and say delta t tends to 0, then f delta of t. So this is something which is a very small step, and this is something which we call as instantaneous frequency, or wi of t in radians per second, angular frequency. So we are interested in this instantaneous frequency when we are talking about frequency modulation. So the instantaneous frequency omega I of t or fi of t is basically equivalent to the general angle over this interval. Now from this we get an explicit expression of instantaneous frequency with respect to the generic angle. So that is omega I of t is nothing but d by dt theta of t, the generic angle. Or also this theta of t is an integral minus infinity omega I of lambda d lambda. For simplicity of analysis, in the forthcoming discussion, we will set this theta naught, the intercept, equal to 0. So now this brings us to the two types of angle modulation, namely the frequency modulation and the phase modulation. So in frequency modulation, the instantaneous frequency is directly varied with the message signal m of t. That is the instantaneous frequency wi of t is directly varied with the message signal wc plus kf m of t. So this is the message signal. This is the argument which was left after taking the derivative, as we have mentioned over here. So if you take the derivative over this point, this line would be exactly similar on this interval as the generic theta of t, right? So over here, what we're mentioning is that if you take the derivative, you would simply have omega c, the instantaneous frequency, right? So this omega c is coming from the instantaneous frequency, and then you add message signal, and then you scale it with a sensitivity constant, which is kf. So the question is, why do we need the sensitivity constant? The answer to that question is that with the message signal, how much you want to increase the frequency or decrease it. For example, in this particular scenario, so if the message signal goes up, by what degree the oscillation should increase? If we reach a peak, so how much increase in frequency should be there? And if it reaches a negative peak, so how much decrease in the frequency should be there? So this is basically governed by the constant kf, right? So this is our angular frequency. But if we're going to talk about the message signal, remember we're going to send a signal s of t through the antenna, which is having a constant amplitude but theta of t. So this theta of t is being varied with respect to the message signal. So the relationship over here is, if you take the integral of it, so you will get theta of t, this would become omega ct, and we would have the constant coming out of the integral minus infinity to t m of, say, lambda d lambda. So that would be the angle. And so if we are sending the message signal, say s frequency modulated signal, so we would have a cos omega ct plus kf m of lambda d lambda, right? So this is basically our fm. Similarly, when we're talking about the phase modulation, in phase modulation, the angle is directly varied with message signal m of t. So by that, what we mean is that this theta of t is simply omega ct plus, originally we had theta naught, but I have mentioned that we are making it 0. We are considering the intercept at 0. So this is just generic. You can keep it, you can remove it. It's up to you, right? But what we're doing is we are directly changing the phase. We are adding something over here. So this is something which relates to the change in phase, and then we are multiplying it with a constant kp, right? So the message signal, it directly changes the phase of the modulated signal. So in short, when we're going to send pm modulated signal, so we would have a constant amplitude multiplied by cos omega ct plus kp m of t, right? So this is basic difference between the two. So you may say they are almost the same. One is, they are related by calculus. So one is the derivative of the other one, or other one is simply the integral of the first one, right? So since we got this one, so we also can achieve the instantaneous frequency Wi of t, which is the derivative of this one. So that would simply give us Wc plus Kp, which is constant, so it will come out of the derivative, but now we have m dot of t. So this is something that we will get. So we have now all the relationships. We have the instantaneous frequency, the phase, and the transmitted signal. And similarly for PM, we have the angle, the instantaneous frequency, and the transmitted signal.
Right. So as a summary, we have this table that summarizes the discussion so far, that is between phase modulation and frequency modulation FM. The parameters of interest are angle and the instantaneous frequency. So if angle is basically directly proportional to the message signal, then you would have phase modulation. When the instantaneous frequency is directly proportional to the message signal, then you would have frequency modulation. But you would see that there is a very direct relationship between the two. They are linked by means of differentiation and integration, right? So if you have a generic angle, if you take the derivative of it, you would get instantaneous frequency, right? Next, we will talk about the system block diagrams of both phase modulation and the frequency modulation. Specifically, when we are mentioning phase modulation, let us start with the message signal m of t. So you can observe that the message signal is being multiplied with a constant which we call as Kp. This is a sensitivity constant. So if we are plotting a block diagram, we have a message signal that is multiplied with a constant Kp. Next, this constant, this whole thing is then summed up with the carrier omega c. This omega c is coming from an oscillator. So over here we have omega ct and we have that summation block over here. So once we add them up, then we get this angle theta I of t. Remember, when we send a signal through an antenna, we are sending a cos theta I of t. So that means that we are again multiplying with a gain of a, which is over here. And then we have a modulated signal, that is phase modulated signal. Similarly, when we're sending an FM signal, frequency modulated signal, so we start with the message signal m of t and then pass it through an integral block. So once it is passed through an integral block, we multiply with a sensitivity constant kf. So the message signal is passed through a linear integral, and then after that it is multiplied with the sensitivity constant kf, which is then added with the carrier frequency omega ct multiplied by gain, and eventually you get a modulated FM signal. Both frequency modulation and phase modulation are inseparable. So you could use a phase modulator to transmit a frequency modulated signal. So I would repeat, you can use a phase modulator together with an integral block to eventually generate a frequency modulated signal. Otherwise, you could use a frequency modulator cascaded with a differentiator to eventually send a phase modulated signal. So you could use one to generate the other one, right? So why is it so? So it is quite evident from this block itself. So let's talk about the first case, using a phase modulator to generate a message signal. So starting with the message signal m of t. So if we are going to start with message signal m of t, you pass it through an integrator, and then you get a new waveform. Let's call it m tilde of t. So once you got this, now this becomes your new signal. Now you can put this signal over here and use the phase modulator to eventually generate a frequency modulated signal. So what I'm trying to say is that you could start with the message signal m of t, pass it through an integrator, you will get a new signal. Put that new signal in a phase modulator, right? But since the original signal has passed through an integrator, we would eventually get a frequency modulation. On the other side, if we start with the message signal m of t and pass it through a differentiator d by dt, so we'll get m dot of t. So once you got m dot of t, this is now your new signal. Now if you pass it through a frequency modulator, so you have a differential and then you have an integral over here. So both of them would cancel out. So once they are cancelled out, you will be getting a phase modulated output signal. So it is quite interesting. If you have either of the modulators, you could eventually get both phase modulation and or frequency modulation, but you would need either an integrator or a differentiator. So they are in a way inseparable. I have also previously mentioned that just by looking at a waveform, let's go back to some original slides in the beginning. So what I'm trying to say is once you receive a signal on the antenna, you receive a signal. So if you receive a signal just by looking at these two, we cannot judge whether the original transmitted signal was phase modulated one or frequency modulated one, right? So we need to know which modulator was used in the first place in order to detect.